right, good afternoon, everyone. Welcome back to class. Thanks again for being here. Today we're doing what I think is an exciting part of the course. It's our first graphical method of solving mechanism design and analysis problems. So we're going to be starting we're going to do a light version in lecture today of drawing scaled diagrams and using a ruler, compass, and later we'll also use triangles a lot, drafting triangles, to draw out mechanisms, measure right on them to learn about what's happening within what we're doing. So if you don't have these today, it's okay, but just a little cue for you. To get those, you may want to bring them to lecture. I know it's hard to work on small desks with drafting tools, so you'll do your best taking notes. For problem set 2, you'll want to use these drafting tools for limit positions, which we're covering today. Okay, if you could bring it in here. Bring it in, everyone. Thanks. I still hear some chatter going on. Thanks, everyone. Yeah. Great. Okay, so a few other notes about what's going on in the course. Pitch meetings, a few brave groups are starting tonight. Most of you will be over the weekend or even into next week. Problem set 2 posted, and I mentioned lab 2. That's not starting for a little while, but I mentioned it because today's lecture, I'm going to show you a little teaser from that. So I just kind of want to cue you for thinking ahead. You're going to be doing that MATLAB session in a few weeks. Any questions about anything with the course or projects? You should all have your client feedback now. If you don't, send me an email right away. Let's make sure you have that and your whole team can see that. If you can't see it, go to Quarkus. I put it as a comment for your submission. So talk with your team members if you're not sure if it's there.
Sorry, so are there 2 weeks between every lab?
The entire lab schedule is posted. So you can look on Quarkus. We put a PDF with all of your labs. So you can see your assigned sessions are all there. Yeah, the later ones are a little closer together. Yeah. Okay, so our main topic, as I say, is going to be about limit positions today. And if I can get my computer going again here. Limit positions have to do with the extent of the motion of a mechanism. Okay, and so this is an important way that we can describe the overall behavior of a mechanism in a few simple numbers. So we already have a first way of describing mechanism motion, which is mobility. That tells you about the whole nature of a mechanism. But I showed you some pre-info on these limit positions in the last lecture. And this is a rocker-rocker type mechanism. And this illustration traces out the extent of motion of the input and the output link. And in this case, it's a little vague, which is the input and output. It doesn't matter so much, although limit position usually is the most important or most discussed when we're talking about the output link. You want to know the limits of the output going back and forth. That's not exclusively true, but it's most often the case. This is a mechanism that I introduced in the very first lecture. We saw this in the internal combustion engine, the piston going up and down. Here it's flipped on its side. And we're going to study this mechanism in some detail today. And this is also the topic of your lab 2, MATLAB lab 2, which is going to be about timing, ratio, limit positions, and these topics we're learning today. Slider crank is on the top. And a variation on the slider crank is shown here, where we move the ground, the slide, down a little bit. Move the slide down a little bit. And this, of course, it physically just moves the output down, but it also changes the behavior of the mechanism in a little bit more subtle way, where if you look at if you watch these illustrations play through, you'll notice that the top one is nice and symmetric, right? Of course, the blue link is the input, and it's just going round and round. And the output, as you'd expect, you could draw some triangles and do some trigonometry and write some equations to describe the output motion as a function of the input. And you'd get a sinusoidal relationship. So you have a nice sine wave giving that output. It's nice and regular, back and forth. So if it made like a ticking noise, you could hear it go tick, tock, tick, tock, tick, tock. Nice even output on the green link. That's the slider crank. There's one on the below, and it's a little hard to see when you're just looking at a mechanism if it's a subtle kind of relationship. This one below is not symmetric. By lowering the ground or raising that pivot point, it's skewed. One direction moves a little faster than the other direction. And so we're going to study this in some detail. It's hard to know just by looking at it what's happening. So we're going to make some diagrams and calculate it. And we're going to get to this thing called the timing ratio. Timing ratio tells you about how symmetric is the output motion. If it's a nice clock-like output, tick, tock, tick, tock, tick, tock, that's going to be a timing ratio of 1. Same time to move right as it is to move left. Tick, tock, that's a timing ratio of 1. Other mechanisms will have different timing ratios, which is just going to be a ratio that's not 1. This is a pump mechanism. So this has a motor going around on the inside, which has a little pin that slides through that slot. Okay, and if you think back to the last lecture, that pin moving through the slot should look familiar. It's kind of similar in some ways to that Geneva mechanism. Pin moving through the slot, it's sliding and turning, so you could analyze that and calculate the mobility of this thing. At any rate, let's think about the timing ratio of this. This one's moving fast enough. I think it's a little easier to tell. Do you think the timing ratio is 1? Is it a nice symmetric up-down motion? Or does it move faster in one direction than the other? Actually, I can hear it. I didn't put the audio on. Let's see if it'll play. It's not sending the audio through. At any rate, I can hear it. It's pretty nice. I can tell from listening that it's pretty even up and down. It's pretty even up and down. And if you watch the video and analyze the time going up and down, you could confirm this. This is an example of a mechanism with a timing ratio of 1. Some mechanisms are designed to have extreme timing ratios. Okay, and this type of mechanism is called a quick return mechanism. And the name should evoke timing ratio to you right away. It's designed to move faster, which way? Left, right? Left moves faster, and then slow return to the right. In fact, I have a physical version. It's a slightly modified version. I'm not going to put it up because it's almost the same thing. You can play with that after the lecture if you want to come up and actually work with this thing with your hand and see. I'm trying to crank it as even as I can. Same thing as is in the video, except the slide. The slide is on the left side, or the red link is tilted to the left in my physical model here. At any rate, of course, it moves faster to the left. I watched this video a bunch of times and tried to calculate it. It's around 2. So it takes twice as long to go to the right as it does to the left. So we'd say that's a timing ratio of 2. You could also say it's a timing ratio of 1/2, same ratio. Most people will like to define it as bigger than or equal to 1, but that's not a rule necessarily. That's our timing ratio. Okay, so to calculate timing ratio, or to analyze the timing ratio, we need to know where those limits of motion are. If you're watching this motion and you want to calculate it, you need to find the leftmost and the rightmost positions, right? That's how you would calculate. We have this, we're going to define an equation by that definition there, and we're going to be able to calculate. So our first task is to find limit positions, left and right. So it's here, 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 here. So those are our limit positions. And we're going to do this, and we're going to do this by a graphical method to start. Any questions about the basics here? The concept is not that, I think it's not that unexpected. Finding limit positions is usually the trickiest part of doing this. And so that's where we're going to start today. And the mechanism we're going to study is this offset slider crank. Offset slider crank. So we're going to draw, I didn't give you a worksheet for this one, but we're going to draw and try and draw this to scale, the bottom mechanism here. We're going to try and draw this to scale on our page. And based on the one that we draw, you try and draw it as similar to this one as you can. And we're going to calculate where those limit positions are and use it to calculate our timing ratio. So here we go. I'm going to do it on the page here. I like to work on the chalkboard, but when we're doing scale diagrams, it's hard for me to do on the chalkboard. So I'm going to do it here, and you can see how I use drafting tools to do this as well. Okay, so we're finding limit positions. That's our task here. And so this is going to be, we didn't really define limit positions. This is the minimum or maximum positions of links in our mechanism. Okay, and it only makes sense to define a limit position for a link that's moving back and forth, either rotating or translating. And so that's called oscillation. Okay, if we have a crank, think about defining the limit position of the crank in this mechanism. It doesn't make any sense. It goes round and round completely. There's no limit to it. So we'd say the crank, the blue link, doesn't have limit positions. But the output link, the green one, clearly has limit positions. What about the red one? The red one is moving in a more complex way through space, right? So you could try, maybe you could, depending on what you're trying to do, let's say the output of the mechanism was actually the red link, and something was attached to that, and you were using the angle of that red link as an output in some machine. You could define the limit position as the two angles, the extreme angles of the red link. Anyway, you need to know what the output is to define what's the limit position of interest. Okay, so usually we'd say it's commonly referred to the output. This actually. Commonly looking at the output link. Okay, and it can be an angle or a position. All right, so we're going to draw our offset slider crank mechanism here. So let's do this. There's quite a buzz going here. I don't know if it's going through the speakers as well. Is it irritating to you as well? Computer audio. Oh, that's a good. Let me try. It's not the computer audio. There's a whole bunch of things plugged in here. Ah, it's the power cable to my light. That's weird. Unplugging it didn't fix it, but wiggling it changes the noise. Oh, there we go. It's actually the power cable to my document camera. Okay, it's not buzzing now. I'll try not to touch it. Okay, here we go. So this is our offset slider crank. I'm just going to draw it here. I'm going to draw the slide elevated a little bit. So I'm going to draw it first, and we're going to just draw it in a general configuration to start. So here's the slide. I've elevated it up above the base pivot point. So I've elevated it up, and the slide's going to be up on top. I'm just going to draw the mechanism now. Let me use the same color. Okay, and this is our first time doing a scale diagram. So this is going to be something that we're going to measure. And in real practice, you would start with something that you know. I kind of just hand drew this, and I'm going to measure on it. You could measure your own and have a slightly different one. You know, in practice, maybe you would print one off from a CAD, or I'd give you one in a testing scenario. Is there a question about it?
This is supposed to be a scale diagram of the GIF in the slides, correct?
A scale diagram. The slides have this in there. If you're working on your tablet or computer, it's in there. I just free drew mine, so you could use that one if you wanted. Is that your question?
In the slides, the levels of the bars are switched, so the pivot point is above.
Yeah, that's right. I find it easier to draw this one. If you're working on the slides, you can draw it underneath, a slightly variation, or redo it this way. Yeah. Okay, so here's our output is oscillating. That's this link 4 moving back and forth. And we're going to draw this a few times. Okay, and of course, when we're drawing mechanisms, we need some key points, right? I'm gonna measure out the link lengths in centimeters on my page. You can use my measurements or measure your own, which will be slightly different. The length of link 2, I'll call it R2, was, so I'm just going center to center on those pivot points, is 2.8 centimeters. Length of link 3 on my diagram is 6 centimeters. Okay, and the offset is how much higher the slide is than my pivot point. But this is easy to make a mistake. The key point is this turning pair, not the slide itself, right? That's where the action is occurring. So we actually want to measure, if we're thinking about offset, we're going to measure the distance up here. That's our offset. Offset distance. So I'm going to measure that 1.6 centimeters. Okay, it doesn't matter how big I drew the block. If the block was a little bit taller and the slide was lower, the key thing is where that turning pair is moving. So when we're going to draw this mechanism again in its left and right limit positions, we're going to be tracking that point, and so we can talk about them. I'm going to give them some names here. Let's call this point turning pair between 2 and 3 is called B. And this point between 3 and 4, that turning pair we'll call C, just so we can talk about them. Okay, so when we're drawing, the reason that a compass is really nice for drawing mechanisms is that we very frequently have links which rotate around a fixed point, like link 2. So point B is going to follow a circular path. And so we can I'm just going to sketch it lightly on here. Just set my compass to the right length. Right, B is going to follow this curve. If you don't have one, you can just sketch a circle in your notes. On the homework and exam, you can do it more accurately. Okay, what about point C? Those are my 2 points of interest. Everything about drawing this mechanism comes down to, once you've drawn the base and the ground, it comes to putting B and C on the map. So point C, it doesn't move right along the slide. It moves along this red line. Right, so it's slightly above the slide. So C moves along this path. Okay, simple enough. So this is the basics. You're going to use our ruler and compass, and we're going to find now the left and right limit positions of this mechanism. So I'm going to start a new page. Depending on where you are on your page, you can decide to start a new one or not. But we're going to draw 2 new diagrams. The first one's going to be the left limit, and the second one's going to be the right limit. So up at the top, I'm going to draw the left limit position. And then halfway down the page, I'm going to draw the right limit. And I like to do them one on top of each other, because I know that my mechanism's moving left-right. The output's moving left-right. So this will allow me to line everything up vertically and measure and compare these positions to each other. Okay, so to start, I'm actually going to draw the ground pieces. So the ground pivot in that slide. So we're not going to line up with the previous one. I'm just going to put them in here. There's my ground. I know that the offset was 1.6 centimeters. So right here, that's going to be where point C lies along this line 1.6 centimeters above. And the ground is going to be just below that. Okay, so point C moves on this line. Okay, 1.6 centimeters above the base. Okay, and in a midterm or a final exam scenario, I would probably draw this for you, because that's like the environment that you're setting your mechanism into. Or maybe I'll give you part of it, the key parts of it. Okay, so now our task is to put link 2 and 3 on here, which basically means finding out where is B and where is C. We know C has to be on that red dotted line. And let's find where B needs to be. And I'm just going to use my compass. I know it needs to be 2.8 centimeters from the base. I've already set my compass. Okay, so that's my 2.8 centimeter radius. And point B is on this line. It's somewhere on this circle. And if we're looking for our leftmost limit position, okay, this is where the links are going to be pushed all the way, the output's going to be pushed all the way to the left. So let's actually watch the video. Of course, I put my computer to sleep to silence the noise. So let's watch it and try and identify what's the relationship between links 2 and 3, that's the blue and red ones, when the green is all the way to the left. So let's let it go. Here's the right, but we're worried about the left. And this is a mirror image, of course, from what we drew. Here it is right there, right? That's the leftmost position. It's when link 2 and 3 are up on top of each other. I would call it like anti-parallel. They're parallel but in opposite directions. Okay, so let's do that. Let's draw that out on our linkage. So that means the point B is going to be back here somewhere, right? And then link 3 will come up to that line up here. So how do we figure this out? Basically, we're going to use our ruler. And we know our dimensions are 6 centimeters. R2 was 2.8 centimeters. Okay, so what I like to do when sketching these mechanisms is trying to do it accurately, is do a rough run first. So I'm going to do up here a very rough version of the same mechanism. Right, it's going to look something like that. That's my rough sketch, just so I can kind of get my bearings and figure out how I'm going to put it on there accurately, right? I'm going to have to basically, link 3 and link 2 are on top of each other. So what I really want to know is, what is this distance? This distance here, right? That'll allow me to find out where on this red line I need to put everything. Okay, so that distance, of course, is R3 minus R2, length of link 3 minus link 2, which is 6 minus 2.8 gives us 3.2 centimeters. Okay, so I need to find from the base to the red line is 3.2 centimeters, and that'll get me over to point C. So I'm going to put 0 at the base pivot and turn my ruler until I hit the red line at 3.2. Right there. So that gives me my location of C up on that line. Okay, and if you're not sure what I did there, I'm trying to recreate that little sketch up there, and just using some basic link geometry to do that. You may have a little bit different way, and different mechanisms you'll have to figure out some other way of doing that. We can add our links in now. I'm going to draw link 3 as blue, comes down to here, to point B. Just so we can see it, I'm going to do link 2 in green, because they're back up on top of each other here. And then, of course, I'll just add my slider up here. That's our link 4. And that's our key point C. Okay, so that's our left limit position. I just did some geometric figuring here to find out where point C should be in this case. And every mechanism is going to have different geometry, but they're always going to come down to some simple triangles. And you'll try and isolate which are the key points and find out where those positions are. Any questions about finding our left limit? The right one's actually easier. The right one, we're going to watch our video again. Okay, right one is right there. So it's when link 2 and 3 are parallel, but in the same direction, both pointing off to the right. There's our left. Now it's moving right there. I kind of missed it. But link 2 and 3 are parallel for our right limit position. So let's do that. And let's put right underneath our left limit position, I'm going to put the right limit position. So I'm going to use my ruler to draw a nice line down. Okay, and actually I should use a triangle. I don't have a large triangle, I have a small one. I'll give it a try. I want to put this right underneath so that I can measure off of it. Let me use it. It's nice to use graph paper or lined paper so you can line things up easier. Not necessary though. So there's my base pivot point right underneath the other one. And just like before, I'm going to go up, what is it, the offset, 1.6 centimeters. And that's where my line of action of C is going to be along here. Okay, C was on that line. I'll just put the ground in here as the slide. That doesn't need to be so accurate. And now we have what we need. So now we need to figure out how do we put links 2 and 3. So I'm going to do a rough sketch. Just a real quick one. So I can figure out what do I need to do for adding and subtracting link lengths. This is where links 2 and 3 are parallel to each other, right? So to find out that distance, I just add R2 plus R3. That's going to give me this distance right there. So R2 plus R3, that's, what are my lengths? 2.8 and 6. So that gives me 8.8 centimeters. So that's the key number that I need now to draw accurately onto here. So I'm going to get my ruler. This point C here needs to be 8.8 centimeters from my base pivot. So I'll put 0 point on the ground and rotate my ruler until I get 8.8 lining up with the red line right up here. I'll just mark it with a dot and then put that circle there. Okay, so that's what we have to do to find point C. And I'll draw the slider. And a common question I get in the course is what happens when they fall off the end of the slide, right? I just drew this ground approximately. So we kind of assume, right, I mentioned before, when you're making drawings, assume nothing weird is happening, like links falling off, unless you know that it's supposed to happen. So I just extended the ground. The left limit position, of course, is way over here. It would have fallen off over here maybe even. So the ground is just there. You assume it's kind of infinite length as needed, unless you know it should fall off, which isn't that common. Okay, so now I need to add my point B along here. So both the links are going to lie right along here. And B should be, what, 2.8 centimeters out. Here's my point B. And I'll use the same colors as before. Green for link 2 and blue for link 3. Okay, now I have my mechanism in the right limit position. Any questions about drawing that? This is about the simplest mechanism that you would need to draw. But what we did here, those tricks that I used for sketching them out is you can deploy for most mechanisms. You just have to figure out what the key points are and what the key triangles are that you're looking at, and add up and subtract some link lengths to get what you need. Robin will do some examples in tutorial tomorrow, additional examples of limit positions for more complex mechanisms. And we're going to look at this one with some more detail. We're not going to do a more complex one in lecture today. The last thing that we need to calculate in our last 20 minutes here is our total goal is finding where the limit positions are and using it to calculate our timing ratio. So this is the limit position. We could actually compare these. I'm going to just draw some guidelines here that I'm going to use to compare our left and right limit position. And we're going to find out how far does this mechanism move. Point C is our output. It moves between these two positions. And this has a special name, which is called the stroke length of a mechanism, is the motion extent left to right. And we can just measure it. So we're doing a graphical method. So I can use my ruler. I measure that 5.8 centimeters for the one that I drew. That's called the stroke, left minus right limit position. If your output is an angle, your stroke would be two angles minus each other. You'd get a new angle. Okay, the limit position itself, you'd have to define relative to some point. So if you wanted to define mathematically or give a number for where the right limit is, you could say, okay, let's say I'm defining the position of C as the horizontal distance from my base pivot. You have to make up a reference point of some sort. So let's do that. Let's add our position of point C in the right limit. Let's say it's how far right of the base are we? And I'll call that x of our point C. And you could measure that out and report that, 8.5 centimeters. Okay, and we could do it for the left limit position as well. Any questions about these terms? Just kind of defining these limit positions. Oh yeah, the question is this point C left limit happens to intersect here. That's just by chance. Yeah, just by chance that it hits with point B there. Yeah. Just by chance. Ignore that last little piece there. Any other questions? Yeah. Sorry? Yeah, this one is an extent, moving left and right as a position. If the output was like a 4-bar rocker, you'd measure the angle and report that. So like the initial angle? You could calculate, yeah, initial to final is 60 degrees. That's the stroke, 60 degrees. Okay, yeah. Thank you. Okay, let's move on to the main event, which is calculating the timing ratio. Timing ratio. And I'm going to show you a little teaser from the Lab 2. Okay, so I'll take your question in a minute. So this is our Lab 2, a little teaser for you. I've sort of solved a similar version of Lab 2. It's not exactly the same as what you're going to do. And I'm just going to run the code, which plots out the motion of a slider crank. So there's a slider crank, and if this one has a 0 offset, right? That point C, it's not labeled, but our point C, in this case, it's moving up and down. But there's no offset, meaning it's right above the base pivot. And in fact, that's defined in the code. A is the offset, and I've set that to equal 0. Okay, and this code nicely plots out. This is something you're going to have to do is the piston position as a function of the input rotation. So the input rotates one full clock, and you get this nice output. Okay, in this case, we get something, it looks like a sine wave, a cosine wave, depending on where you define your 0 angle, right? It's really exactly a sine wave, really nice and symmetric. Left and right motions, or in this case, up and down motions, are the same. So I'm going to replot this and change the offset. Let's give it a little bit of offset 4. I'll run it again. There we go. The crank goes round, 1 rotation. Boom. We get, it looks at first glance identical. But if you look a little closer, especially look at the very top at 0 and 360, you see it's a little asymmetric now. The beginning, it goes down a little slower. And the minimum point is actually shifted over a little bit. It's not 180 anymore. It's like 186 something. Let me put it over even more. I think the biggest that makes any sense, I'll put it to 13. So really big offset now. So now the slide has been pushed way over to the right. Now it's really asymmetric. Right, what do we see here? Now the peak over here has moved over to 10 degrees-ish. The base, the lowest point here, has moved over to 240. And over here, we don't even get to the peak, right? So it's a cyclical motion, so this would repeat if it kept going round and round. So there's a peak at 10, a trough at 240-ish, and the next peak will be at 370, right? 370. So this is one way we can find limit positions, simulating the mechanism. In the background, there's some equations that calculate all this, right? So a third way you could use to find limit positions is looking at those equations directly. And we're going to do that later on in the semester as well. But I'm going to show you how we calculate what I keep referring to as the timing ratio. And we're going to see how we could use this plot. I'm just going to re-sketch this plot so you can remember that. We're going to re-sketch that and use it to find the timing ratio. The timing ratio, and this is, roughly speaking, how symmetric is the output motion? Okay, and that, whether or not this is an important measure for your mechanism, your machine, depends on what the output's doing. If this was a musical instrument, of course, the timing is everything. If you want it to go, a metronome to go tick, tock, nice and even, you'd design your mechanism to have a timing ratio of 1. If you want your metronome to go tick, tock, that'd be a timing ratio of 2 or 3, right? Other mechanisms are going to have different functions. Let's say you have a machine which is picking up boxes and putting them onto a counter. Pick up a box and put it on the counter. To be as fast and efficient as possible, maybe you want to pick it up slowly, put it on the table, and then quick get back to the beginning and grab the next one. Put it up slowly, quick get back to the starting point, pick up the next box, and put it up on the conveyor belt. So that kind of thing is really common, where there's one direction of motion which does the task, and then the mechanism quick resets. And this is sort of a classic one which is used a lot. This quick return mechanism does exactly that. So you'll see this one appear a lot. It's pretty simple, and it's easy to change the timing ratio by adjusting some of the dimensions in here. You'll study that one in the tutorial with Robin. That's going to be one of the problems that he talks about. But let's calculate this for our offset slider crank based on that diagram. So timing ratio, let's write an equation for this now. I put up on the slide earlier the definition, which is the ratio of the time to move left or up divided by time to move the other direction. So a little more general, we'd say time to move one way divided by the time to move back. Okay, and usually we'd be talking about the output. So we'd calculate this for the output link or the output point. So we're going to calculate this. We're going to calculate some times, and we're going to use that diagram, which we saw in MATLAB. We're just going to sketch it here, and we're just going to do it kind of approximately. But we saw those, the key numbers, right? We plotted the vertical axis was the position of the slide, position of the slider, x4. And the horizontal axis was rotation of the input, theta 2. Input rotation. Okay, and the important thing about theta 2 is we're assuming that it's rotating constant, at a constant speed or constant rate. And of course, that really affects the timing ratio. So timing ratio is best defined or makes the most sense when you have a constant input. The crank is a motor, and it's just going round and round at a nice constant speed. And we're going to study how the output moves in response to that. If you have a non-constant input, you'd have to think about this a little bit more clearly. But we can calculate. We know the rotation rate. Let's say we know that in advance, theta 2 dot. Rate of change of our angle theta 2. That's the time derivative of theta 2. So if we wanted to calculate what theta 2 was, it would be theta 2 dot times whatever the time is. So we're going to say this goes from 0 to 360 for our offset slider crank. Okay, and there were a couple key points on there. So I'm just going to sketch that out real quick from what we saw. We saw that there was a max at 10 degrees. We saw that there was a min at 240. And we saw that the next max didn't occur till 10 degrees. After 360, that was like 370 was the next max. And I'll just connect these. For what we're calculating, all that matters is the top and bottom points. So the connection, we're not too worried about it for what we're studying right now. Okay, so that was the motion. During this section, it's moving, was it moving up or down during this? Link 4, that's our output. I think it was moving down. Okay, and during the second phase of motion, from 240 to 370, it was moving up. Okay, so those are our two phases, the up and the down phase. So the down phase is from theta 2 equals 10 degrees to 240 degrees. And moving up had theta 2 from 240 to 370. And 370 is the same as 10 degrees because it's a cyclic input. Okay, so this is how we're going to define our timing ratio. Is we're going to find out what's this span, what's this distance measured in time, divided by this distance. So that's going to be our timing ratio. And we're going to rely on the fact that our input is constant. So that means that if we measure things in angles, it's going to be proportional to the amount of time. Right? Theta 2 constant means angles are proportional to our time in this case. Okay, so let's calculate these things. Our timing ratio, let me define this, what we're trying to get to at the bottom here. Our timing ratio, it's going to be amount of time elapsed to move one way, we'll say down, divided by the amount of time to move up. Okay, and I was just talking about how that constant input rate is important. So we could define, right, here's our equation relating time to the angle. So if we wanted to find delta time, the amount of time that's elapsed, we could say time we divide by theta 2 dot. So we get how much angle has elapsed, we'll call it delta theta, divided by theta 2 dot. Okay, so that's derived from this equation here. Just dividing by theta 2 dot. And we're talking about an amount of time elapsed. That's why I call it delta. Amount of angle, which has changed. Okay, so we can plug this in now to our timing ratio equation. In the numerator, we get, I'll put it in parentheses, delta theta down. I'll call it delta theta d divided by theta 2 dot. In the denominator, we have the up version. Delta theta up divided by theta 2 dot. But theta 2 dot's a constant. That's our constant input. So those cancel out from our equation, which is great. We get this nice simplification by tracking the amount of angle that's changed up and down. It's equivalent to tracking the amount of time that's elapsed. So let's just find these two angle changes, which we can measure from above. 10 to 240, that's delta theta down, is 230 degrees. That's the amount of theta 2 rotation. During the moving up phase, 370 minus 240 gives us 130 degrees. And these should add up to 360, right, for full revolution. So our final timing ratio then comes to the ratio of these two, down divided by up, 230 degrees divided by 130 degrees. Timing ratio, that comes to about 1.77. So it spends almost twice as much time moving one way than it does the other. Not quite. 1 1/4, 1 3/4. Any questions about this? Yeah, we'll just take 1 or 2 questions and then we'll be done. Oh yeah, so it's an important question. Why did I put down on the top and up on the bottom? You could do the reciprocal. Most people like to define this just greater than 1. But if you defined it as the inverse of that, that's fine as well. We're just out of time, so if you have any other questions, we'll revisit this in the tutorial tomorrow with Robin. Thanks, everyone.